Hello everybody, and thank you for joining me. Root Beer here with question 23 on the Fermat paper from 2005. A solid cube of side length 4 centimeters is cut into 2 pieces by a plane that passed through the midpoints of the 6 edges as shown. We got midpoints and we got the 6 edges arranged around here. By symmetry, I'm going to say this guy is a regular convex hexagon. To the nearest centimeter, the surface area of each half cube created is... Alrighty. So I can sort of think of 2 ways to do this question. One, I could just pick one of the half cubes and compute its surface area. And the other one, if I each of the half cubes has an equal amount of the surface of the original cube showing. So I'll figure out the original surface area, divide that by 2. Each half cube gets that amount plus the hexagon here. Okay, I think both of those are equally good strategies. This is a fantastic question where props can help you, depending on what proctor and where you are and what contest rules say. You can bring in little props, and I have in the past recommended, wooden shapes if you're a really extreme prop person. Other things you can do is, scissors and some blank paper and some tape, and you can create some interesting things. But I actually have one prop here. It's a cube that I got for Christmas, and it's the cuts on this puzzle. It's like a Rubik's cube. Cuts on this puzzle are such that you turn on the half. So actually, the halves here on this cube are exactly the surface area. So this would be the perfect sort of puzzle to help you visualize and say, okay, well, I need to count up this bit and this bit and this bit to get the surface area. And you can actually, it's going to be kind of hard, but if we trace our finger, it's the same length everywhere, and it actually is a hexagon that we are rotating, a regular hexagon that we've got there. So that'd be fine. It'd probably be a bit more helpful if you guys had a cube in your hands. But this is exactly what I'm talking about when props can help you, and it's just an accident that I happened to get a cube recently, is what these guys are called, that would perfectly help visualize this prop. Okay, I didn't have one in 2005 or anything like that. I didn't even know how to solve a Rubik's Cube back then, but props good. Anyways, we can still approach it without props. Doesn't matter which method you use. I think the slicker one would just be to figure out the surface area of the hexagon and then the surface area of the cube and those sorts of things. So that's what I'm going to approach it by. But you could also just, as we've got our cube here, you can just, figure out the tiny little triangle here and this triangle here and this half bit that is really just a side without one of these triangles, that sort of thing. I don't know if I was holding that properly for everyone at home to see. Doesn't matter. We're moving on. The prop is going away. I'm not touching it anymore. Alright, so here's my plan of attack. So each half has surface area equal to half the surface area of the cube plus the area of that hexagon. Okay? So how do we calculate surface area of a cube? Say a cube of side length 4 centimeters. Well, you can actually go a little better and do surface area of a rectangular prism, which is twice, so 2 times the length, 2 times length width plus the length times the height, plus the width times the height. Now, on a cube, the length, the width, and the height are all the same thing. So this is 2 times 4 squared plus 4 squared plus 4 squared, or 6 times 4 squared. So that's 6 times 16, 96. Okay? So this guy here, the whole cube has 96, so half of that goes to each of the 2 halves that were cut. So 48 is the surface area of the cube. Then we also need the area of that hexagon. So 96 over 2 plus the area of the hexagon, which is really 48, plus the area of the hexagon. And the hexagon is not small and not trivial. Now, they did ask us to the nearest square centimeter, so I'm thinking we're going to grab our calculator at some point. That is a prop that you always should have. But if we take a look here, C32 is right out. B48 is likely out because there's almost no way this hexagon has less than 1 unit of area. So we're looking at things like 69, 65, and 58. And if we start to get an intuition of how big the hexagon is, we can likely narrow it down. I'm betting it's probably A or D, but right now it's sort of a guess out of 3 if they called time, and that's something to be aware of. So now we need area of the hexagon. That's the real hard part for this question. So I'm going to draw a bigger diagram. We're trying to get a handle on this hexagon here. So we have the midpoints of these 6 sides. Okay. So, midpoints there. Is there a fast, a slick way to do this? I can't see a very fast way to do this, so let's start labeling things. So we've got 4 as the side, so we've got 2 here, and 2 here, and 2 here. So we've got a right angle on this side, so we have a right angle triangle. Both of the legs are size 2. And we got the orange guy here. So by Pythagoras, 2 squared plus 2 squared, which is 8. This guy's going to have 2 root 2 as a side. Okay. So we might say by symmetry it's a regular hexagon. You might just guess that it's a regular hexagon. There's lots of ways you could view this one. But, what's the best way to talk about this? If I were to connect up opposite points here, they're on opposite edges, so they should all go through the center of the cube. And so if I drop another right angle, these guys are going to be side length of 4 of the cube, and then my dashed line here is then going to be 4 root 2, again by Pythagoras. I'm not going to write it out, but so now we have hexagon here. And I know his side lengths are 2 root 2. But because these opposite lines here all go through the center, they all go through the same point, they go through the center of the cube, and they're all 4 root 2. If I have them, we get 2 root 2s, and so we get a whole bunch of equilateral triangles. So many that you can now confidently say, yes, this is a regular convex hexagon. Not completely important to know that, because now that we've got it written as 6 equilateral triangles, so we just need 6 times the area of the equilateral triangle of side length 2 root 2. Okay. Well, how do we get the side length, or how do we get the area in terms of the side length of an equilateral triangle? So equilateral triangles are also isosceles triangles. So if I drop an altitude here, splits the base in half. Now we have a right angle triangle. And so our height here, h squared is s squared minus s over 2 squared. So that's going to be 4s squared over 4 minus s squared over 4, 3s squared over 4. So h is going to be root 3 s over 4, or no, over 2. And so the area is going to be 1/2 base times height. Well, the base is s, the height is root 3s over 2, so we get root 3s squared over 4. You can check that out, and this is a formula that works for any equilateral triangle. Maybe you already knew this, but if you didn't, there you go. So so the area of the regular convex hexagon is going to be 6 times root 3 over 4 to root 2 squared. 6 times root 3 over 4, well, this guy's 8. So this is 6 times root 3 times 2, 12 root 3. That's the area of our hexagon. So the area of our half cubes is 48 coming from the half of the original surface area of the cube plus 12 root 3. And what is that approximately? Well, here's where we grab our calculator. Root 3 times 12 plus 48 is about 68.784. And we want it to the nearest centimeter, so we round up, thanks to this 7, to 69 centimeters squared, and that was A, I believe. Yeah. So that gives us an answer of A. Not bad, not bad. The alternative method that I suggested of, let's see if we can go back to one of the pictures. So the alternate method that I suggested was we'll use green to sort of figure out the area of one of these triangles. How many of those triangles are on this side? 1, 2, 3 of them. And then what else do we need? Well, we need this this big area here on the top, and there's 3 of those as well. And then you also need the area of the hexagon. You can break it up like that, because the big green area is just the square, so 4 by 4, minus one of these small triangles. So as soon as you have the area of that small triangle, you sort of have this one plus a green, and this one plus a green, and this one plus one of the big greens. So you really do get 3 of the side lengths of the, or 3 of the sides of the cube, which you can calculate pretty quickly as 48. 3 times 4 by 4. Alright, but however you did it, you should get 69 when you round up. And yeah, that does it. So we've got question 24 on deck. We're going to flip the page in anticipation of that question. Thank you guys for watching. Like, subscribe, all that, gobbledygook. But thanks for watching, more importantly. Keep practicing your math, and good luck on any math contests you happen to be writing. I'll see you for question 24 in the next video.